Session overview talks for parallel sessions 3 and 4. We'll get started with Renee Weber, who I believe is remotely presenting about lunar geophysics and magnetics overview. Are you out there, Renee? Ah, there you are.
Brian, can everybody hear me?
We can, thank you.
Your introduction cut out, but I trust it was glowing.
As always.
I'm sorry I couldn't make it there in person today. Let me just share my screen so I can pull up my slides here. Okay, can everyone see my slides okay? I'll take that as a yes. All right, so I'm here to introduce the parallel session on lunar geophysics and magnetics. And given that the talks in this session largely focus on magnetism, thermal emission, and volcanism, I thought that I would focus mostly on deep internal structure of the moon. And before I start, I just want to thank Ian and Matt, who both gave me slides for this presentation. All right, here we go. So geophysics is one of the most direct ways that we can elucidate the deep lunar interior structure. And interior properties provide the constraints that we need to understand lunar formation and evolution. These include things like the layering, composition, seismic velocity and density, the presence of or not of partial melt, and the state of the core, state and layering of the core, so liquid, molten, partial melt layers. And these things also provide possible indicators of an early dynamo for magnetic field generation. And the image here is the picture taken from the New Views of the Moon 1 interior structure, where you can see those layers, you can see suggestions of possible seismic discontinuities, and we'll talk a little bit about that later. But constraints on these properties overall come from seismology, from heat flow, from geodetic parameters and lunar laser ranging, from magnetic induction studies, and from studying the moon's gravity fields. So there have been a lot of recent reanalysis done on the Apollo data, and also obviously GRAIL, Lunar Gravity Mission, taught us a lot about the moon's internal structure. But our understanding prior to this was basically that we know the moon has a structure similar to Earth, where it's differentiated into a crust, a mantle, and a core. But we also know that the moon's moment of inertia is roughly approximated by a homogeneous sphere. So if there is a core, we know it has to be pretty small. And you can see I've drawn some question marks on the image on the right to indicate that there are a lot of different constraints and uncertainties in those constraints on core layering. So I'm just going to step through each of the measurement types, starting with seismology. So the two pictures here are cross sections of the moon. So if you assume that the Earth is sort of up, we were in Apollo fortunate enough to have seismic stations that were all deployed on the near side of the moon. And those stations did not detect any seismic energy originating from the far side of the moon, which indicates either that the far side of the moon is aseismic, which seems unlikely, or that there is a highly attenuating core that's just keeping seismic energy from the far side from propagating to the near side. And also the deep moonquake source regions were found to be in a region, the deepest ones, approximately 1,200 to 1,400 kilometers deep, which also can place constraints on the size of the core if it exists. So lunar laser ranging, another an indirect measurement, which is basically using the retroreflectors to place precise constraints on the moon's geodetic parameters, and ranging began in 1969. So dissipation provided the first lunar laser ranging evidence for a fluid core, and then based on some assumptions on the composition of the core, you can put rough constraints on its radius. And I also just want to point out that as of today, lunar laser ranging measurements are sort of right on the cusp of being able to discern the presence and size of a solid inner core. Another indirect measurement is magnetic induction. And we have some constraints on magnetic induction from Lunar Prospector. In 1998, the orbit plane of Lunar Prospector was nearly parallel to the sun-moon line, which made it optimally oriented for making measurements of the induced moment as the moon goes in and out of the Earth's geomagnetic tail. And if you assume that this induced field is caused entirely by electrical currents at the surface of a conducting metallic core, you can also get a constraint on the core radius. And again, by making assumptions on its composition, you can determine how much mass of the moon that core consists of. So recently, we had the GRAIL mission, and also some work of mine and my colleagues reanalyzing the Apollo seismic data. So obviously we know from GRAIL, GRAIL pretty much got extremely tight constraints on shallow structure. So basically the structure of the crust, global structure of the crust. But I want to point out that those thickness measurements are still tied to ground truth seismic estimates from the thickness of the crust at the Apollo landing sites using the seismic data. And those estimates are uncertain. So looking at the deep structure from Apollo seismic data from my work and those of my colleagues in 2011, found evidence for core reflections in the seismic data. So that would be seismic energy that, rather than traveling directly from the source to the surface, instead also travels down, interacts with the core, and reflects back to the surface. And there was evidence of layering in the core. There was evidence of a solid inner, fluid outer core, and a partial melt layer at the base of the mantle. And the GRAIL mission produced a family of core models that are consistent both with geodetic parameters and these seismic constraints. But as of today, there are differing perspectives on whether or not that partial melt layer is really required to satisfy all available constraints. And the arguments for the presence of a partial melt layer include things like inverting mass, moment of inertia, the tidal love numbers, inverting those things, and electromagnetic sounding data and phase equilibrium computations, joint inversion of geodetic and seismic data, and then also numerical simulations of the viscoelastic response of the moon, which has been used both to argue for and against the presence of a partial melt layer. Other arguments against a partial melt layer focus on the distribution of water in the lunar interior and the resulting effects that it would have on the electrical conductivity and tidal dissipation. So that's sort of a remaining question mark that we have about the deep interior. And I just want to point out that these measurements also have synergy with geothermal measurements. So geothermal measurements track the heat production and the interior temperature distribution of the moon. We know from Apollo that, well, both of the Apollo heat flow experiments were in an area that was dominated by this thorium-rich crust, which is considered sort of an anomaly. And how this came to exist really depends on the internal structure of the moon. So determining the physical and thermal structure of the core and the deep interior is really critical for understanding the moon's formation and subsequent evolution. And we know that geophysical data can also help constrain the lunar dynamo, which the moon may have had and may have generated and maintained its own magnetic field through the dynamo. And then, of course, these geophysical data also provide context in the presence of a core and a partial melt layer and dynamo and convection provide context for thermal emission and volcanism studies. All right, so both deep structure and magnetism, surface magnetism, have bearing on the lunar dynamo. We know that magnetism is ubiquitous in the solar system. We have measured it from orbit on the moon. And also by doing sample analysis of returned samples where we have observed natural remnant magnetization in the samples that have been returned. And the figure on the right shows the sort of picture of the paleo intensity in these samples as a function of time before present. And we can see that early in the moon's history, there was a period of time where there was a relatively high paleo intensity. And each one of these lines here shows an estimated maximum lifetime that the moon was able to sustain a dynamo using these different dynamo mechanisms. And we don't really know the nature of the extinct lunar dynamo, and it's somewhat surprising that it even existed on such a small body. And there are still no published numerical models of dynamo generation, and of course, dynamo would have implications for lunar thermal history and the state of the core. So the lunar dynamo, you can constrain the lunar dynamo with paleomagnetism, and you can also constrain it via crustal magnetism studies. So on the left, there is a picture of one of these enigmatic and very beautiful magnetic swirls. And we don't know the origin of these. We don't understand how they form. And this is roughly comparable with our ignorance of the seafloor anomaly that were observed on Earth and our sort of state of knowledge of them in the 1940s. So when we think also about magnetic studies that constrain the interior structure, we can refer back to global scale magnetic induction studies. So the mantle temperature at global scale could be measured with a pair of orbiting magnetometers. And this was demonstrated at single points at the Apollo stations. And electromagnetic sounding of the moon performed during Apollo also provided constraints on core size, mantle composition, and the interior temperature. And the lateral heterogeneity in the electrical conductivity constrained by these types of studies is consistent with the presence of the PKT. And so the figure on the right, you see this simulated electrical field due to background magnetic field oscillations, which highlights this warm conductive region at the PKT. And so if we go back to my sort of very simplified cartoon of the internal structure of the moon, on the left we have a picture depicting a possible scenario via which this sort of global dichotomy in interior structure and large-scale upwellings are producing melt over the history of the moon. And how do we sort of develop an internal structure model that is consistent with a model like that? Remembering back to the fact that the moon's moment of inertia is roughly approximated by a homogeneous sphere. And one way to do that, of course, would be to be able to go back to the moon and get more data. And so I'm ending my presentation with a plug for the Lunar Geophysical Network, which, if you don't already know, is a network of geophysical nodes, a minimum of at least 4, that operates continuously on the surface for an extended period of time. And I've highlighted a few different studies and proposals, past and future, that advocate for different numbers of stations and different lengths of time. Looking back to the International Lunar Network, that was about 2 years. Net baseline 4 years. And you may have heard of durations as long as 10 years being suggested for future lunar geophysical networks. The payload is a suite of instruments consisting of a seismometer, heat flow probe, a retroreflector, and a magnetometer. The seismometer would really be used to understand not only the current seismic state, but also the detailed internal structure. And obviously, the more instruments you're able to deploy, the more detailed that structure will become. A heat flow probe would be used to characterize the temperature structure of the lunar interior. A retroreflector increases our ability to determine deep lunar structure. Remember, I mentioned before that we were close to being able to determine the presence of a solid inner core using lunar laser ranging analyses alone. And if we could increase the number of retroreflectors and increase the footprint of the retroreflector array, we could better determine deep structure and also conduct tests of gravitational physics. And finally, a magnetometer allows us to use electromagnetic sounding to measure the electrical conductivity structure of the lunar interior. And that's the end of my talk. I hope I was able to sort of set the stage for the presentations that will follow, and I'm happy to take any questions.
Great, thank you so much, Renee. It's a fabulous overview talk of the current state of knowledge of geophysics. We do have time for a few questions, and so that she can hear your questions, please come up to the microphones in the center of the aisles. And while we wait for the rush to come up to the microphones, a quick question for you from me, Renee, is if you were designing your own missions and had the opportunity to put seismometers anywhere on the surface of the moon, are there any specific target sites that you would go after, or are you just after seismometers on the surface anywhere?
That's a great question. I would first refer you to presentation on this exact topic that I made at the Lunar Landing Site workshop a few months ago. Mm-hmm. However, I would point out that, like I mentioned before, we have no seismic measurements from the far side. So I personally would very much like to see a seismometer deployed on the far side. Obviously, that introduces some additional mission constraints in terms of power and communications. But there are a lot of different factors to consider when you're thinking specifically about seismology, where you want to go. We know very well where active moonquake clusters are, so if you want to guarantee that you will observe a moonquake, it would make sense to put them somewhere near one of those. If you were to attempt to record seismic waves that traveled through or interacted with the core, also we can use ray theory to predict which clusters would produce core arriving phases or core interacting phases at a given location. And we can also, I've also made maps that sort of take that into account. So there are a lot of different things to consider, but overall, I would be happy with a seismometer anywhere on the moon.
Fair enough. We have two questions. We'll get started with Jack Schmidt.
Jack Schmidt, Renee, great summary of a lot of information. One thing I would suggest is that we think in terms of adding to the general model a lower mantle as well as an upper mantle. The upper mantle having been defined pretty much by the Apollo seismic information that we have, at least from the front side. And the lower mantle, there's, I think, increasing evidence that it represents the protocore of the moon, one that was originally quite cool and chondritic in composition, with water and other volatiles contained that we're now sampling with the pyroclastics. The other, another thing that I would mention is that your upwelling might well be represented by the overturn of the original upper mantle by the dynamics introduced by a basin-forming event called Procalarum, just something to consider as another hypothesis relative to the upwelling. And then finally, we have some evidence of in addition to the remnant magnetism and the work that Ben Weiss has been doing with samples recently, but in the low maturity regolith that covered the ash at the Shorty crater, we see evidence also of a global magnetic field preventing maturation or significant maturation of those of that material. Just some additional things to add to your picture.
Yeah, I didn't include a figure here to show the different structure models, but many of them, especially the ones that are based on these inversions where you kind of throw everything in the kitchen sink at it, don't show a lot of indication that the mantle is, you know, that the one-dimensional structure of the mantle is essentially constant velocity. But again, it could just be because of the sort of paucity of seismic stations. We would really need a lot of really well-distributed and high number of seismic stations on the moon to be able to do those sorts of, you know, tomographic studies that would let you look at lateral heterogeneity as well.
Well, one of the things we need, though, is a source of the unusual volatiles in the pyroclastics. And you need a lower mantle that has a significantly different volatile composition at least, or where those reservoirs of volatiles can exist.
Great. Thank you. And one final quick question from Bill Botke.
Okay, I just have a quick question, which is Ben Weiss and others have been noting that the magnetic field seems to be surprisingly long-lived on the moon for a body its size. Do you have some thoughts about why it could be long-lived?
I mean, that's a great question. I might even defer that to some of the later speakers because it's sort of outside the realm of things that I've thought too hard about. But again, if you go back to this slide showing these different models for core dynamo generation and sustaining that over time, we haven't really decided on as a community which one is the best one or the most realistic one.
Okay, great. Thank you, Renee. One final round of applause.